What I'd like to do is talk a little bit about the global warming potential and internal curing and why details matter and why we really need to think about what our overall mission is when we're specifying things like global warming, low global warming potential. I'm going to skip through these things. They're in just for the people who look at the slides that are up online. But the basic idea here, and I think we've heard some of this throughout some of the other sessions, in 2010, internal curing really begins to become used. Now, if you look back through the literature, in the late 1990s, the early 2000s, there's a lot of research going on in this, but it's really around 2008, 2010, where people start putting this into bridge decks. And the overall goal of this is really to reduce cracking. And you may say, well, why would we want to reduce cracking? Is cracking really a problem? This is the underside of a bridge deck, right? And some of you may say, that's very attractive. Somebody got up there and they painted those white lines every 2.5 feet. No, that's calcite that's coming through cracks in those bridge decks, all right? And why is cracking such a big issue? Well, it's a big issue because it allows aggressive agents to get in, mostly chloride ions, mostly other things like that. So when we start to look at this, we don't want to lose sight of the important aspect of internal curing, which is reducing cracking. Now, to demonstrate why this is so important, what we've done here is we've instrumented a large restrained slab. So this slab is about 15 feet long. It's got a reinforcing bar that goes through it. And if you get up close, really close to this, what you'll notice is we've actually drilled holes through the reinforcing bar and put little tiny probes along the length of the bar. Because what we want to figure out is when it starts to crack, how much of the bar actually starts to corrode. Because there's an argument that's put out by some people that says, well, the crack is only a little tiny piece of the bar. It's not that important. Don't worry so much about cracks. All right? What I want to point out is the plain concrete sample, right? The concrete that the DOT was happy using as their standard concrete cracked at 3 days in this test. It was a glorious crack. There was much rejoicing when it cracked. The internally cured concrete didn't crack. Right? The one that cracked, the plain system, went into corrosion which within 4 days of salt being applied. So if you can think of a situation where you've put out a new bridge deck, it cracks at 3 days, and 4 days after salt is applied, it starts corroding. What is the service life of that concrete? Right? We're starting a problem, right, by allowing those cracks to exist there. So one thing I do want to mention is the other item is many of these cracks, they come down to the reinforcing bar, as you see up here with the epoxy, all right, and they go along the length of the bar. So when we actually measure what's corroding, we see it's not just at the crack, it extends several inches to a foot back from the edge of where the crack is because you've now started to open up some of that debonding along the bar. So you've really created an environment where that can fill up with the de-icing salts, the de-icing solutions, and you can really start corroding a substantial portion of that bar. Again, I want to point out that the internally cured concrete, no cracks, so we're actually worried about a diffusion-based problem, which we'll talk about in a few seconds. Now, earlier this morning, there was a lot of questions on what's the best test to use to measure your transport properties. They all give you similar results. All right? If you like the RCPT test, if you like the NORD test, if you like the stadium test, you want to do resistivity, you want to do something else, they can all be correlated back to each other, and then they can be used in service life models. The big takeaway from this, though, is we've heard about internal curing is going to increase the reaction of the cement, the SCM, the biochar, the fly ash, whatever else is in the system. It's going to increase that reaction. By increasing that reaction, you reduce the porosity of the system. The second thing that you do, especially when you use lightweight aggregate as your internal curing agent, you get rid of interfacial transition zones. So if this is your normal sand, there is a region around the sand that can be porous that can allow things to move through it fairly quickly. When you have an expanded lightweight aggregate, it's an expanded calcined clay, calcined shale, or calcined slate. Those calcined materials will react with calcium hydroxide and form hydration products, That happens at the surface of the aggregate, so you no longer have this interfacial transition zone. The surface of the aggregate is actually reacting with the calcium hydroxide, densifying it, so you actually lose those interfacial transition zones. And now you have a case where you may have poured a 0.43 water to cement ratio concrete, but it behaves like a 0.36 because you've reduced those interfacial transition zones. You've cut down on that preferential path. You can use this information, as I mentioned. These are actually done with a full life cycle model using ionic transport, using stadium or a similar type of an approach. And the basic issue here is, if you use that conventional concrete, it's going to crack at around 18 to 22 years, or it's going to start to corrode at around 18 to 22 years. But this is only where the concrete doesn't crack. When you couple together the fact that you have cracking, this moves way over here, and you start that corrosion process much earlier on. And many DOTs are replacing bridge decks much more rapidly than they need to because they're corroding the reinforcing steel, right? And they're having to get out there and replace these. In the cases where we have internal curing, we have substantially increased the time to corrosion, plus we've reduced or eliminated that cracking potential. So now we're doubling or tripling the service life of the concrete. So again, our overall goal was reducing cracks. By using this with some SCMs and getting additional hydration, we're also improving the resistance to chloride penetration. Right? And just to show that it's not just one lab test, these are surveys. This was a survey done using Kansas's data and looking at some of the bridge decks that were done in Indiana with internal curing. Right? What you notice is here are where the bridge decks were that are internally cured. Here's where the typical bridge decks are in terms of crack density. I see a trend. I don't know if anybody else does. All right? Substantial reduction in cracking. Right? So I'm always amazed when we do another survey and we find out that cracks are a big concern for DOTs. There might be a solution here to reduce cracking in bridge decks. Again, this has been talked about and people have shown the actual equation. The real trick is we're replacing a portion of the sand. So lots of people say, is this going to behave like concrete? Yes, we've replaced a portion of the sand with porous sand that's water-filled. Right? It is very similar. In fact, one of my favorite comments on one of the bridge decks we poured, they asked, why are you here? Because there's nothing going on with this concrete. And I was like, that is the perfect time for me to stop coming out to watch these test slabs. All right? We were sent to provoke people in New York State, right, to ask them what are the limitations with internal curing. So the industry put on a very nice lunch, and I kept trying to ask questions, and I kept trying to ask questions. I was getting no response. And finally, a contractor said, you know, the biggest problem we have is when weenie researchers interrupt our lunch. And I said, if that's the biggest problem we have with placing this concrete, we're in a good place. All right? It looks like regular concrete. It places like regular concrete. All right? Greatly reduces cracking and extends the life of the concrete. But the question is, how does this now tie in with the industry's push to reduce global warming potential? Right? Now, you may look at this graph and you may say, I've never seen a graph like that before. Right? This graph is just a graphed version of NRMCA's Athena data that relates compressive strength and the global warming potential. Now, I will mention compressive strength is not a good indicator of the global warming potential of a mixture. Right? There are lots of other things that you can do to describe a global warming potential. Further, all right, what we're starting to see are desires to reduce that global warming potential. And in fact, we've heard a lot at this meeting about ACI 323, which says thou shalt move this blue line by some amount alpha to get to the green line. Right? So the question is, how do we start to do that? Well, if we sit down and we take one of those standard INDOT bridge deck mixtures that we were looking at before, we can go through and put in all the data. And there's a couple things that we can talk about as we do this. We can put in all of the aspects of the mixture proportions, right? And this happens to be something very similar to the FHWA spreadsheet that Tim mentioned earlier. and we can put down the global warming potential numbers. If you get up really close to the screen, what you're going to find out is about 90% of this mixture comes from the cement. So the goal is reducing the amount of cement clinker in the mixture, using SCMs, reducing the cement content, doing other things there. Right? It's also not surprising when we plot this particular mixture next to that data, really close to the NRMCA line, because for years there were recipe specifications that the DOTs used, right? And they all used very similar mixtures, right? So what could we do to reduce the global warming potential? One thing I want to mention before I start to talk about that is, because we're just plotting this in terms of compressive strength, there's absolutely no difference between the elevated slab that was talked about before and this slab that's going to be exposed to de-icing salt. They have different exposure conditions and probably should be designed slightly differently. All right, so we have to think about the role that exposure conditions play when we start talking about global warming potential. So one thing we could do is we could go through and we could actually take out cement and we could replace it with slag and silica fume, right? And we could reduce our global warming potential. We could go from 273 to 227. We have now moved to the green star. Well, that's awesome, right? We dropped it down, all right? We had that magical line that's down here. That's great. But at the same time, we accidentally improved in performance, right? So there's probably more we could do here if we really want to reduce the global warming potential by moving this, all right, back over. But now, if we really wanted to internally cure our concrete, we can add internal curing to the system when we move to the pink triangle. Right? And there's going to be a lot of people sitting here going back to the first comment that was made when this session was started. Whoa, I don't want to use internal curing. It raised my global warming potential. Well, let's get into some of the details on this and think about this a little bit more. Because initially, it seems like a great solution to pick the green star, right? That's the lowest number. That seems like a good idea. Well, there's a lot of things that seem like a good idea, right? Grabbing the stick and hitting the lion here seemed like a good idea until the lion got annoyed, right? We just talked about the fact that there are many benefits of the internal curing of the system in terms of long-term durability. We said that compressive strength is not enough, and here's a secret. Neither is A1 to A3 global warming potential. They are not enough to describe where we want to get to as an industry. Internal curing is reducing transport, and it has substantial benefits, right? And these benefits are not only in the lab, these benefits have been demonstrated over the last 15 years in real life. These have been demonstrated through computational models. There's substantial benefits to this approach, all right? So when we think about the current way that we look at life cycle assessment, ISO says the standard way we should look at this is considering all these things throughout the life of our concrete, right? We should consider the production, the construction, the use, the end of life. My favorite is the afterlife, right? We're getting into the afterlife. This is awesome, right? But what we've done is we've made this very simple with our EPDs, and we've simply said, let's forget everything in gray. Well, we're missing a big part of what happens in the concrete. It's a little bit like playing, does anybody remember the game show, This Is Your Life? Right? Where they would bring somebody up and they would have somebody come up. It was his grade school teacher, it was his college teacher, right? Somebody knew later on, and they would have to guess all the things that happened. We're playing Guess Your Life by graying out this part, all right, of somebody's life. Right? This is the equivalent of what we're doing with only considering A1 to A3. So if we take this a step further, all right, what I want to do is I want to come back to this and I want to start to think about some simple ways we could look at these mixtures without having to do the full LCA. Right? And I think there's a little bit of logic if we start to look at this. Now, if we do that computational modeling for those three mixtures I showed before, the plain conventional mix, the mix where we did the slag replacement, and then we did the internal curing, here you see the strength that jumped up, but you also see that we got substantially lower RCPT numbers or substantially reduce transport. When you do service life modeling, that translates into a substantial difference in the time to corrosion. You add about 8 years to where those two lines intersect, right? You add about 8 years to this, that's when you're replacing the bridge deck. If it never cracked. If it cracked, you're way over in this area. And I was shocked. The first time we started doing this, we're telling people you're going to be replacing decks at 18, 20 years. And they said, yeah, that's about when we replace decks. Right? It's shocking to me that we're replacing the decks that quickly. So a couple of things that we could do is we could look at those numbers that we saw before, all right, and we can say we've got the global warming potential, 273, 227, 277. But if we actually just stopped and thought about, what if we just took this number and divided it by the time of corrosion? Does that change how we might view these numbers? Well, that's this number right here. Global warming potential per year of corrosion. 9.8 to 4.4. Over a 50% improvement when we look at that. If we looked at this, we learned earlier that Tim told us that 75 years is the life cycle, all right, that people are expecting from a bridge deck. If we thought about this over a 75-year life cycle, we get to replace this deck 3 times. We're going to be really good at it at 75 years. The global warming potential is not this 273 because we got the opportunity to do it 3 times. Right? This number is almost 3 times as high. So we are substantially higher than if we had just used our internal curing mixture. Now, we could actually go through and we could do a full LCA analysis. Right? And this is some work that actually did this, considering what would happen if you implemented these decks in the city of, in Minnesota. And what they were doing was they were essentially starting to look at what the impacts were in terms of travel time, in terms of costs, in terms of repair safety, all right? And they only use a minimal fraction of the impact of travel time. So I want to point out that they're using about 2% of the actual user costs when these calculations are done. So for the plain concrete, all right, we may see a number around 20. This is that NDOT conventional mixture, right? If we go to a high-performance concrete, we see that cost may be higher. But when we start using those internal curings, we see these numbers dropping down substantially, and we see us not out there replacing these. From a safety perspective, we're putting 1/3 less workers in the way of traffic, right? 1/3 less traffic jams, right? We're fixing bridges a lot less. We're keeping the roads smoother. There was a discussion earlier about smoothness related to emissions. Substantial improvements when we look at this holistically. So again, I want to just point out, are we headed in a great direction to think about sustainability and global warming potential? Yes. But there is more to life than just A1 to A3. Because we might make the wrong decision here. We might be the monkey that picks up the stick and smacks the lion. We really need to be figuring out different ways to think about how we incorporate materials that are more durable, more long-lasting, or provide other ways to bring value into the system. A full LCA is the way to go, but there's a lot of people who say, oh, that's way too hard. Let's come up with a simpler way that we can get into that. Right? So again, industry is focused on reducing the global warming potential of concrete. Great step forward, but let's not lose sight of the goal. We want sustainable, long-lasting structures with a low global warming potential. EPDs can be great, but they're only considering A1 to A3. Right here, there's a lot of discussion now. We're going to bring in A4. We got a lot more to do before we get excited. All right, we got to get into B, C, and D. All right, we can make poor decisions if we only use A1 to A3. Right, we've seen already some very low carbon mixtures that have gone in and lasted 3 years and being pulled out and being replaced. We have to think about the long-term durability. We have to not only focus on strength or GWP. LCA is where we need to be. Internal curing has numerous benefits. All right, I want to just thank lots of people who pull all the data together, right? Because it's the data that's been gathered over the last 15 years that allows a lot of these conclusions to be made. So with that, I will take us back to the project where they didn't think it was worth me being there because there was nothing interesting going on because this was just conventional concrete, even though it was internally cured. All right? And we'll take questions if people have questions.